got a little summary of the first class on here and a little summary of what we plan to do for the second class on here. Remember from the first class, spent some time introducing Python coding, and we talked about variables and assignments and operations and input output. We used as a illustration or as an example gravity, and specifically we used the free fall law for gravity, and we used the circular orbit law for gravity as two simple trajectories that emerge from the law of gravity and laws of motion. The idea there was that those two examples, so the free fall law and the circular orbit law, are really kind of the tip of the iceberg of the things that we can explore and the things that we can examine with computational numerical techniques that are difficult or impossible to explore with analytical techniques. So the idea was as kind of a stepping stone to the world of numerical computational physics and what you can do in numerical computational physics. In today's class, I want to introduce some more Python that we need. This is basically the remaining Python that we need. We need what's called control statements. So control statements are statements that affect the flow of the program, and the control statements that we'll talk about, there's just a few of them, are if statement, we'll talk about the while statement, and we'll talk about the for statement and the break statement. So that's the Python code I want to talk about. As a example of things to apply these control statements to, I picked a couple of other basic physics topics. Just like free fall and circular orbits, these are topics that you meet in your first physics class. I'm going to use projectile motion as an example, and I'm going to use also pendulum motion as an example. These are also like part of the tip of the iceberg of the world of the law of gravity and the laws of motion and all the phenomena that emerge from the interaction of bodies under gravity and the resulting motion. So that they're also like free fall and like circular orbits, kind of the simplest solutions to that problem, the most analytically amenable solutions to that problem. And so that's why I'll be using those as examples. We'll also be taking kind of our very first steps, getting a toe in the water of analytically solving differential equations, for example, for many body problems. So we'll start doing that today, and we'll see some of the problems with doing that today, and we'll introduce I didn't write it on this slide, but we're going to introduce the Taylor approximation, Taylor expansion. That will be an important tool for us to do numerical computational solutions of many body differential equations. That's the plan. Okay, so I just want to say a few words about kind of analytical pendulum motion and projectile motion, and beyond the world of analytical pendulum motion and projectile motion. And this is going to be the basis for us looking at the control statements, the ifs, the whiles, the fors, and so forth. So this is just one little slide of simple pendulum motion that you meet in elementary physics class. From a sort of theoretical point of view, right? If you put together the pendulum, the simple pendulum, the mass of the pendulum experiences, if you displace it away from the equilibrium, experiences a restoring force. If you put together the law of gravity that's providing the restoring force and the laws of motion, you can build a simple second order differential equation. That's this differential equation here that you're probably familiar with. So that describes the simple pendulum. And the solutions of that differential equation for the angle of the pendulum, the displacement of the pendulum, are kind of this elegant set of solutions. They're sinusoidal solutions of the oscillating pendulum, simple pendulum to and fro. I wrote that solution down here too. There's a characteristic frequency of the pendulum that depends on the length of the pendulum and the acceleration of gravity. That's the omega naught on this slide. There are parameters in this solution here. It's really a infinite family of solutions, of elegant solutions. The parameters are the amplitude and the phase of these oscillations. And the amplitude and the phase are determined by the initial conditions that you release the pendulum with. And so this is the simple pendulum. But no real pendulum is a simple pendulum. Real pendulums experience additional forces beyond the gravitational force, restoring force. They'll experience like damping forces, they'll experience general driving forces, and their motion is much more complex and in general is not amenable to analytical solutions. We're going to have to do numerical solutions. I just listed on here some of the features that we'll explore in later classes with real pendulums that are not features of motion with simple pendulum, and are not explorable in general analytically. So one feature that we'll see with a real pendulum is that if you swing the pendulum from large enough, with a large enough amplitude, with a large enough angle, then the motion is not sinusoidal, first of all. It's more complex than just a sine wave or a cosine wave. And secondly, it's not isochronous. So its period now depends on the amplitude. And so those are two features that emerge for a real pendulum, unlike a simple pendulum, and we'll be able to explore that computationally numerically. So that'd be kind of interesting. Another interesting effect, the second bullet that I put on here, is that in the presence of damping, you can get a kind of splitting of the motion of the pendulum, or a bifurcation of the motion of the pendulum into two types of motion. One which is has a periodicity to it, an oscillation to it, and one that doesn't have a periodicity or an oscillation to it. That's the over and under damping that you've probably met. And so we'll be able to explore that world again, numerically, computationally. Another feature, this is typically we'll explore this when you have a driving force, but another feature that you get with a driving force is that a feature that's called period doubling. So if you drive your pendulum, if you push the swing with a certain period driving force, you can get pendulum doubling, which is the appearance of not only that frequency in the motion of the pendulum, but double that frequency in the motion of the pendulum, or double that period in the motion of the pendulum, or 4 times that period in the motion of the pendulum. That's called period doubling, where in addition to the driving period in the motion of the pendulum, you see a pattern of other periods in the motion of the pendulum, which are 1, 2, 4, 8 times the period of the driving force that's pushing the pendulum. So that's a very interesting effect. You have to explore that numerically, computationally. You can't explore that analytically. Another thing that ultimately emerges for a pendulum is chaotic motion. So chaotic motion, by chaotic motion of the pendulum, we mean it is deterministic motion. There's nothing indeterministic about it, but it's unpredictable motion, kind of like the weather. It's unpredictable after a long period of time. So we'll be able to explore that chaotic motion of a pendulum. Again, the only way to do that is numerically computational. So that's the world of things that are coming up. I said I'd say a few words about the other example we use today is periodic motion. So again, projectile motion. Projectile motion you meet in your first general physics class, and a projectile motion in the absence of air has a simple analytical solution. The projectiles follow a parabolic path described by a parabola. Sort of more formally again, the solution of projectile motion, which is motion under gravity, obeying the laws of motion, is described by a second order differential equation or coupled or pairs of second order differential equations describing the horizontal and vertical motion that are built out of the law of gravity and the laws of motion. And I just wrote down again these two second order differential equations here for the horizontal and the vertical motion. Here's the acceleration of gravity. Those simple second order differential equations have simple, well-known solutions that we know. They're these equations of motion that I've written down here. And so this is kind of for simple projectile motion in the absence of air resistance or other forces, there's kind of this elegant solution that the motion is a parabolic trajectory, a parabolic path. And these are the equations for that parabolic motion. And if you want to solve, for example, for the range of the projectile or the duration of the flight, knowing the position that you release the projectile and the velocity that you release the projectile with, you can use these general solutions to the differential equations describing the projectile motion and solve for your flight time or your projectile range. For any real projectile, unlike that ideal projectile, there's no simple, elegant solution. Rather, again, we have to use numerical computational techniques to solve projectile motion in real situations, say for a golf ball or for a missile. You're going to use simulations, computations to solve the motion. And on here, I just listed a few of the features that we'll explore for projectile motion that you can only really access computationally and numerically. The trajectories, for example, are not parabolic trajectories of those elegant, simple projectile motion. The motion exhibits things like terminal velocity. So that's a feature of projectile motion in the presence of air resistance, in the presence of air drag. There are different regions of projectile motion that correspond to different regions of two numbers. One of those numbers is the Reynolds number, and one is the Mach number. So one region, two of the regions for the Mach number are kind of subsonic and supersonic motion, whether you're below or in the region of the speed of sound. And so the solution to motion in these different regions is a computational, a numerical problem. Also with the Reynolds number, different regions for the Reynolds number in projectile motion would correspond to either the kind of laminar flow through the air or turbulent flow through the air. And again, to solve those problems is a problem of computational numerical physics. So this is sort of, again, the world that you can explore numerically, computational, can't explore analytical. Okay. Right, I'm about to go on with actually introducing the coding and the control statements, but I just want to wrap up here with a few statements about the example I'm going to pick. I'm going to pick for the if statements, I'm going to pick an example related to the bifurcation of the pendulum motion into a region of overdamping where there's no periodic motion and underdamping where there is periodic motion. So that's going to be my kind of if statement example. For the for and the while statements, I'm going to pick an example from projectile motion. And I'm actually going to make our first step towards solving numerically projectile motion. So I just wanted to say a few words ahead of that, how we're going to go about doing it. We're not going to do it this way, right? So the analytical approach is to construct this differential equation out of the law of motion and gravity, then to find the general solutions of the differential equation that you built out of the laws of gravity and motion, and then to tailor that general solution to your particular situation, your initial conditions, and solve for your, I don't know, your flight time of the projectile or your range of the projectile. So that's the method we kind of know and love from other classes. What we're going to do is our first steps on a numerical approach to solving the motion of the projectile. And the way that we're going to do this is, firstly, we're going to take good old continuous time, smooth continuous time, and we're going to discretize it as if it's just a bunch of steps or ticks in time that are separated by some little time interval, some little tick. So we're going to take continuous time and we're going to discretize it into individual little steps in time, intervals in time. Knowing the position of a projectile, velocity of a projectile at some tick, let's say I'll call it Ti, tick Ti. It might be tick T1 or tick T2 or whatever it is. So tick Ti, I'm going to calculate the estimate the numerically the coordinates of the projectile, the position and the velocity again, at the next tick, Ti plus 1. So if I was thinking, I know the position and velocity of the particle at T1, I'm going to calculate position and velocity of the particle at T2. Once I know it at T2, I can calculate the position and velocity of the particle at T3. So that's going to be the procedure for figuring out the trajectories numerically. Is just once I know the initial condition for the particle's coordinates, position and velocity, I can calculate its position, velocity and coordinates, position at the next tick of the clock. And then once I know those, I can calculate the position and velocity of the particle at the next tick of the clock. And this is going to be a great way of introducing while loops, for loops. So we're going to use that as the example there. I'll leave to the code the details of how I'm going to calculate the change in position from one tick to the next tick, but basically it's because I'll know the velocity and the acceleration of the particle. I'll use the velocity and acceleration of the particle to calculate the change in position and the change in velocity. Okay. So let's go to introducing the code. So here's my Google Drive, and actually this is I'm going to make this bigger. If you remember last class, this is what I did in the last class. So this is the directory I made. We did that Hello World program, and then we looked at the free fall law, and we calculated the distance fallen or the time taken to fall based on variables and assignments and operations. So I'm gonna, I think I'll just make a new notebook here. And I don't know what to call this, pendulum discriminant. And I'm going to call it that because I'm going to show you if statements, actually if, else if, and else statements for the application that I mentioned where if you have a pendulum with damping, its motion can kind of split into these two different landscapes, or these two bifurcate to these two different landscapes. One way you've got periodic motion, and the other way you don't have periodic motion. And there's kind of a point, a boundary between the overdamping and the underdamping case. And this is very important in kind of in engineering, for example. You know, in a car, you want to sit real close to that boundary between the periodic and the between the over and the underdamped case, between the non-periodic and the periodic case. Because if you sit right there at that critical region, that's where, you know, if I drive in the car and I drive over a speed bump, I'm not seeing it. My wife always says, "Why didn't you see that?" So I drive over it. We want those vibrations to die away as soon as possible from going over the speed bump. And so they design the suspension of cars so that they're at damping is close to this criticality. That damps away the motion of the suspension as quickly as possible. And so this is very important in engineering. This is also important if you build a bridge or you build a house or you build a building, right? And you want to make it so that it doesn't fall down if there's an earthquake. So you don't want the building or the bridge to fall down. Again, you want to understand, you don't want it oscillating a lot to and fro. So you want to stay away from the underdamping. Again, they tend to build it either in overdamping. So if the building shakes or the bridge shakes, it slowly returns to equilibrium without causing any disruption. Anyway, so I'm going to calculate the quantity, I'm going to call it the discriminant, that distinguishes between the overdamping and the underdamping cases and tells us where critical damping lies. So for the case of a linear damped pendulum, there's two parameters that determine the discriminant. And so let me just define those to begin with. One of them, I've already mentioned it, is omega naught is the symbol we normally give. It's the natural frequency of the pendulum. And I'll just give that assign that some value. So it's a frequency, yeah.
So can you enlarge it?
Oh, yeah. Always tell me to do that because I'm looking at the screen. Oh, the screen's a little large. Why can nobody else see in it? Okay, is that large enough or do you want to? Yeah, okay. So this is the frequency. This is angular frequency, radians per second, which is, if I divide it by 2 pi, it'll be the frequency in hertz, oscillations per second. But this is a characteristic of a simple pendulum. All simple pendulum have their natural frequency. This one happens to be a frequency of 1 radian per second. So the units here are radians per second. The other parameter that's important for discriminating between over, under, and critical damping is a parameter that's often called gamma, called the damping coefficient or the damping parameter. So it characterizes the size, the scale of the damping force. So the bigger the gamma is, the bigger the damping force. The smaller the gamma is, the smaller the damping force is. And I'll make that a small number, relatively small number. And these two numbers for a linear damped pendulum determine whether you're going to live in the world of overdamping, you're going to live in the world of underdamping, or you're at this special case of critical damping. And so they determine whether you've got periodic, non-periodic motion, for example. What specifically determines that? Well, this is the discriminant. And the discriminant is the difference in the squares of these two numbers. So it's gamma squared I guess I could have actually squared it. Less omega naught squared. And so that is the discriminant. If that discriminant is a positive number, that's the case of overdamping. So that determines that you're going to get overdamping, you're going to have no periodic motion. If that number is negative, that's the case of underdamping. You're going to get periodic motion. And if that number is 0, that is criticality. That's the critical point. And that's often an engineering target, that critical point. And so it's very important in engineering, also in electronics, these come up, to be able to determine whether you're in over, under, or critical damping. And so that's why I'm using an example, I guess. Okay. So we're going to use the if statement to determine, we're going to use if, else if, and else to determine which and print out which of these conditions we're in. Are we positive, negative, or are we 0? So let's first test if we're positive. And I think I better write this and then talk about it rather than try and do both at the same time. Okay, so this line of code here is a control statement. The control statement has that I'm using here is the if control statement, and it has some partners. I'll mention them in a moment, the else if and the else. It has the format of the control statement, then a condition that's going to be tested. So the condition I'm going to test is whether the discriminant is above 0. So if it's positive, it's going to test that condition. And that test is ended for a control statement by this colon here. And whether that condition is true or whether that condition is false is going to determine whether this following line is code is executed. So if this is true, then we're going to execute this code here. If it's not true, then we'll go on. And we're going to go on to the next control statement. This is, I say else if, but it's actually written as if. And in this one, I'm going to test whether the discriminant is negative. Actually helped me with everything, didn't it? Wrote the whole code for me. So again, has the format of the control statement, the condition that I want to test. Now I'm going to test if discriminant is negative. This is going to correspond to underdamping. And I end that control line with a colon here. And if this is true, then I'm going to execute the indented code below it. And I'll print out that this is the underdamping case. And if it's false, I'll just go on. And you can actually have, I've got one else if statement here. that's testing whether the discriminant is negative. But you could have many else if statements. Have a whole stream of else if statements, if that makes sense for your application. My application here, it doesn't make sense to have a whole list of them. Final member of the if family is this else statement. An if statement can only have one else statement. It can have many else if statements, but it can only have one else statement that I'm ending with here. This indicates, again, there's a control, this is the control statement. This is the control command, and this is the colon that you always end a control statement with. But there's no condition being tested here. Unlike the if statement and the else if statement, there was conditions being tested. There's no condition being tested there because you're going to execute the following line, indented line of code in that case, if none of the if statements or else if statements were true. And so this is a convenient way of using if, else if, and else to look at the discriminant that I've calculated for my particular pendulum and determine whether I've got a condition that is either overdamping and non-periodic motion, underdamping, periodic motion, or I'm at this critical point. I got critical damping. And so if we run this in this case, it's telling me it's underdamped. I've got underdamping, and it's underdamping because, well, look, this quantity here is 0.1 squared minus 1 squared. So this is going to be negative. It's this statement that is true. We've got the case of underdamping. If I was to increase the damping coefficient or the damping constant up here, the gamma here, right? This would be then a case of overdamping. Now that gamma squared minus omega naught squared is a positive number, that discriminant is a positive number, and I've got overdamping. And if I was an engineer and I'd arranged that gamma was 1 in this case, then that's the case where the discriminant is 0. And so this little code here figures out that this is the case of critically damping. So this is an example of how you might use if, else if, and else statements to discriminate different states of your system, whether you got over, under, or critical damping, and therefore execute different code. Here, the code I executed was just to print out the fact. But in another program, you might be executing different code whether you got under, over, or critical damping. The point here of our control statements is that unlike the coding we did in the first class, where we basically went through the code line by line by line. We did line 1, executed that. Line 2, executed that. Line 3, executed that. These control statements, if you think about them, are allowing you to make decisions about which lines you execute and which lines we don't execute, or allowing the code to make decisions about which lines are executed and not executed here. So which of these are lines, these print statements are lines that can be executed. We're selecting which ones to execute with the control statements. And that's what control statements do. They make decisions about which lines are going to be executed. That's for the if, else if, and else. But we'll see with the for and the while, they also allow you to execute lines of code multiple times. That's what for and while are about. Any questions on that one? Okay. So let's leave that code behind. Let me title it, otherwise. Oh, I did title it. I guess I'll go to refresh. I'm going to now go on to the while statement and introduce the while statement, which, as I say, is a way of controlling, executing a line of code or lines of code multiple times based on, again, a condition. So we'll take a look at that. Where am I going here? I'm going to make another notebook. I'll give this a name. So I'm going to take this example for the while statement and the next example for the for statement from projectile motion. So projectile. And what was I going to calculate? That's actually a good question. I'm going to calculate the duration of the flight of the projectile. And I'm going to do it with a while statement. I'm going to do it also with a for statement, I think. So I'll make that distinction here. Okay. I've got to do a little bit more coding here. I've got to set up a little bit more variables because I've got to set up the problem, right? Of the projectile motion. So I'm going to imagine on Earth, where the acceleration of gravity is 9.8 meters per second squared. Look, I'm not putting comments when I write this code. And I should be putting comments when I write this code. In the examples on the in the notes in Canvas, they have comments in, but standing up here, if you were to wait for me to write comments as well as the text would be here to sometime in the evening. So I'm skipping a lot of comments when I write the code. But here's the acceleration of gravity in meters per second squared. There's another couple of parameters I want to define, which is the I'm going to focus on, for this projectile motion, I'm going to focus on the vertical motion, because I'm going to calculate the duration of the flight of the projectile, and the vertical motion would dictate the duration of the flight of the projectile. I need to define the initial vertical velocity of the projectile. I call that y0, and I need to define the initial vertical velocity of the projectile. I call that v0. I'm going to say I've released the projectile from 10 meters height, so the top of some building, and I'm going to throw it at 15 meters per second. And so these are my initial conditions. Now, this shows you another way you can assign variables in Python. I could have written y0 equals 10 for 10 meters, right? And I could have been a second line, v0 equals 15 for 15 meters. But you can, sometimes it's handy to do this, pack multiple assignments on one line by separating the assignment variables and the assignment numbers with commas here. So that's all I did. This line will assign y0 to the first variable to be 10, the first number, and v0, the second variable, to be the second number, 15 meters per second. So these are my initial conditions that I've set up. Again, I should be really should be commenting this code out, but I can't type in front of class, and there'll be all sorts of typos, so I'm going to avoid doing it. We said the way that I'm going to solve this problem is to take continuous space-time and discretize it, to make it a lot of little individual steps in time. I'm going to introduce a couple of variables for that. The initial time that my clock starts at, I started out at 0, and the time step. This would be in seconds, so this is a millisecond, and that's going to be my little time step. And so clock starts 0, and then I got a tick is 1 millisecond later, then 2 milliseconds is the next tick, 3 milliseconds, next tick, 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 tick. And it's in those ticks that we're going to follow the motion of the projectile. Okay. I'm going to keep track of the trajectory of the projectile, the vertical component of the projectile's motion, with 2 additional variables that I'll just call y and v. So these are kind of the time evolving trajectory of the projectile as time elapses. And I'm going to keep updating these as time evolves. But I want to set them initialize them initially to my y naught and my v naught. So again, this is an example where I can make 2 assignments on one line. If for some reason it sort of makes the code a bit more compact, and sometimes it can make the code a bit more readable if you're putting together, combining things on a line that kind of makes sense as a package rather than making sense individually. Right, now let's get on with the while, introducing the while statement. Okay, so again, I'm going to write this while I didn't really want it to write everything for me. And let me just write a couple of lines here, and then I'll start adding to it. This is an example of why I can't comment in front of you. It would just take so long. Okay, so this is again a control statement. The control is identified in magenta here. This is the while statement. So just like the if statement or the elif statement or the else statement, it's the first thing you start with in your control line. Then we've got a condition. And just like we have with the if statement or the else if statement, we have a condition. And the condition here is going to be that for executing the code is the condition that y is greater than 0. I'm going to use that condition. So let's stand back and imagine what the problem is asking us to imagine. I'm on the top of a building. It's 10 meters high. I'm taking a projectile, a tennis ball, and I'm throwing it with an upwards velocity that is 15 meters per second. I'm going to figure out the duration of the flight of the projectile as it goes up and then comes back down the side of the building. When does it hit the ground? How much later does it run? I'm going to recognize hitting the ground, projectile, the tennis ball hitting the ground by its y value. It's going to hit the ground when y is no longer above 0. So I'm testing whether or not we've hit the ground here. If it's true, we haven't hit the ground. If it's false, then that's the moment that we hit the ground. So that's what I'm using the while statement for physically, to test whether the projectile is still a projectile or whether the projectile is now, on the ground. Okay, so again, it has the statement of the control statement, the condition, and ended by a code. And then below it is going to be indented code that will execute. The thing is with the while statement is that we will keep executing this code. We'll execute these lines, and then we'll execute these lines again, and then we'll execute these lines again and again and again, so long as this condition is still true. But the moment it's false, and the projectiles hit the ground, then then it'll stop executing the code. So stop executing the code when the projectile has completed its trip, and we can figure out how long the time it took to complete its trip. I'm going to fill in a few lines of code here. So the first line of code is, well, look, each tick, remember we discretize time, so every loop around this while loop, every execution around the while loop is corresponding to one tick. So I can keep track of the time by updating the time by the length of one tick every time I go around the code. So every time I go around the code, this statement here is going to increment time, the time variable here, which started out as 0, by the amount dt, the duration of a tick. I can't remember whether I said that I could have written t equals t plus 1. No, sorry, I could have written t equals t plus dt to increment the time. Or you can shorten that if you just want to increment something. I can write t equals plus equals dt. That line is a shorthand for adding the dt onto the current value of time. So I'm pretty sure I didn't introduce that in the last class, but that's an operation that we can do, an assignment and an operation that we can do with just the one symbol. If I had minus equals, it would subtract off the dt every time that code is executed. If I had asterisk equals, then it would multiply by dt every time it executed that line. Okay, so that's updating the time. And the other things that I really need to update are the position of the particle, which is x, and the velocity of the particle. And so here, this is where we do this is really the heart, this is the core of our computational physics, numerical physics, in which we're going to determine the trajectory of the particle. This is where I'm updating the position of the particle for its based on its current position to what it will be after one more tick. And I'll update the velocity based on its current velocity to what it will be after at one more tick of the clock. And the current position and the future position will be different. The current velocity, future velocity will be different because this particle, this object, this tennis ball, is moving, and so its position will change. It is accelerating, so its velocity will change. So the new position is going to be. Sometimes I find it unhelpful to have all these suggestions for what to do. But the new position will be, after one tick, will be the current position, x, changed by v dt, right? V dt is the change in position due to the velocity over that time interval dt. This just comes from, this is just the definition of velocity. Let me make at least one comment. V, as you know, equals dx. I've suddenly changed to x, sorry. V equals dy dt. Velocity is rate of change of position. The change in position, dy, is v dt. So I'm adding on just this little change in position over this little interval of time due to the fact that the particle's moving. I've got to do the same thing for the velocity. The velocity is going to change because the particle's accelerating. The change in velocity is going to be exactly what it just says here. And
that again is just from the definition of acceleration is, right, what is acceleration? Good question. It's dv dt is the rate of change of the velocity. So the change of velocity in some little time interval is going to be equal to the acceleration times the length of that time interval. Okay. And I think that's everything I need. We start out with the initial coordinates, y naught, v naught, for the particle. We enter into this code, and well, I updated the time every time we go around this these three lines that get executed here. So we keep track of the time, and then I update the coordinates, the y coordinate and the v coordinate, because the particle is moving as a velocity and the particle is acceleration of gravity. And so y and v become the evolving trajectory of the particle. And when y evolves to being zero or less, it's hit the ground. And we'll jump out of that while loop. And at that point, I'll just print, let me just print the time. And maybe let me also print y, so we believe it. I don't know why it's taking so long for this, but it's never, I mean, it could be that it's never exiting the code. That's a possibility. Did I get this wrong? Oh, I know, yeah, look. Okay, this is good, exist, stop. I had a bug in my code, right? Well, of course I'm going to have a bug in my code. Every class I will have a bug in my code. What was the bug in my code? Well, I threw the ball upwards and the ball is accelerating in the upwards direction. And so it just races off into space and it's never going to fall to the ground. The acceleration is downwards. So if this positive 15 is upwards 15 meters per second, then I need a negative acceleration here. So let's try that again. And run. And we see that the flight time was 3.6 seconds after I threw it off the building. The final position, yeah, look, it's just the moment that it's crossed the threshold from being a positive position to being a negative position. So this is the indicator that it's hit the ground. So that's an example of a while state. Any questions on that? Beyond that, it is a bit of a hint about how we're going to go about solving problems, say differential equations, numerically, computationally. The way we're going to solve motion, projectile motion, other types of motion, computationally, numerically, is to say, break up time into a lot of little time steps. We're going to start out by knowing the initial conditions for the moving body or bodies. And then we're going to update the initial conditions for the moving bodies at each little time step. It also kind of suggests some of the problems that we might run into as we solve this sort of motion computationally, numerically. For example, if I made the time step much coarser,
then I would get a more approximate result. So I'm going to take big steps if I run it with a time step that's 1/10 of a second. I get a different number. I got 3.8 seconds instead of 3.6 seconds. The earlier one was more accurate because my time interval was really short. This later one is less accurate because my time interval was very coarse. So always in computational numerical work, you're going to be trading off precision against how long it takes the program to run. You know, if you make tiny time intervals, it's going to take longer to run. If you make coarse time intervals, it's going to be less precise. There's a more insidious approximation that's going on here. And it's actually in these two lines, and we're going to have to come to this. I said that the change in the position of the particle in one tick is the current velocity times the time interval, and that the change in position, velocity of the particle is the acceleration times the current acceleration times the time interval. Well, actually, that's not quite right. But the acceleration here is okay because the acceleration is constant, but the velocity is changing. If the velocity is changing, we're using the current velocity to determine the change in position over this time interval. That's an approximation too. And so we're going to spend some time working on better approximations for the situations where the velocity is, where either the velocity, the acceleration, or both the velocity and the acceleration are actually not constant. And therefore, you can't use their current values, or therefore their current values are an approximation to what they were over the true length of the time interval. So that is an approximation. It's actually a very dangerous one, because the error from that approximation tends to accumulate as the ball goes upwards. I'm always overestimating the velocity during the time interval because I'm taking the current velocity at the beginning of the time interval. So I'm always overestimating the time interval. So I'm going to calculate a height that it rises to that is not high, but sufficiently high. So I make an accumulating mistake in my calculation. So we really got to fix that. Okay. I just wanted to show you a for statement quickly. If I'm going to show you. A for statement is another way of executing lines multiple times. But rather than based on you execute and execute and execute based on a condition, in a for statement, you execute and execute based on a specified number of times that you're going to execute the lines for. Let me write this down in range. So this is the format of the for statement, and it has this this format here that has a for and an in, and it's for this I is a variable, and this range here, this is what we call an iterable. So let's start with the last argument here, the range. By iterable, I mean something like a shopping list would be an iterable, right? There's bananas, there's chocolate, there's milk, there's cheese, or whatever. So it's kind of a list. And the for statement will iterate through that list of the banana, the chocolate, the milk, and the cheese. And that's what this format does. And what it does is for each item on the list, it's going to, each time it executes this code, it's going to execute the code with each item from that list. So the first time it goes through the code, for my list, it was started with banana. So it executes it with banana, it goes through the code. Then the next goes through the code with chocolate and then with milk and then short-term memories, not big enough, can't handle 4 things. What was the last one I was gonna? Anyway, it goes through this shopping list, executing each time. So the I values are changing as you walk through here. Now, I'm not using I in this code. What I'm using the format statement for is just to go through the code a specified number of times. The range function that I put here, this creates for me a list. So this function actually builds a list on that line, and it's just a list of numbers that are in, I put a million here, a million, sequence of million integers from 0 to 1,000,000 minus 1 is what that range will do. And so left to its own devices, this code will go through this list 1,000,000 times. Well, this code will be executed 1,000,000 times as directed by this for statement. Now, I don't want to keep, I want it to stop when the object hits the ground. I don't want to, the while statement was better because I could stop the while statement iteration when it hit the ground. So here I go do a little bit more work if I'm going to use a for statement. I'm going to put a additional line in my code that's going to check whether y is positive. Actually, it's going to check if y is negative. Or equal to 0. Actually, AI was better than me. We're going to check the y value as we watch these trajectories evolve. And if y is 0 or negative, then we're going to execute this line. This is also a control statement. It's interesting, it doesn't have the colon after it. And this statement will, you can use it with a while loop or a for loop, and it will cause you to break out of that while or that for loop. Jump out of it. So a for loop is this loop that you're going to go round and round and round and round. You're going round and round and round in a while loop. You're going round and round and round in a for loop. If you have a break statement, if you hit a break statement while you're going round and round and round in the for or the while loop, you're going to leap out of that loop. And it's going to terminate. So a little bit more clunky way, but I've used a for statement, a if statement, and a break statement to do the job I did with just a while statement of calculating the trajectory of the particle, but stopping when it hits the ground. And so let's try executing this. I'm sure there's a bug in it. Yeah, so it ran, and it told us that the particle will hit the ground for 3.6 seconds. That's the duration of the flight. And this is the y value. It's the first y value where it went from positive to negative. Okay, so that's we've now done the if, else if, else. We've done the while loop. We've done the for loop. We've seen how the break works. I think that's everything control statements that there is. I think it is. Let's go back. Any questions on that? I'll go back to the code. I think this isn't the code. I'll go back to my slides. I want to go back to what problems I set up with the pendulum and the projectile. In both cases, we're trying to find the trajectory, say the angle of the pendulum as a function of time, or the coordinates, x and y coordinates of the projectile as a function of time. That's our goal. We know very well how to do that analytically with differential equations and solving differential equations. Here we're trying to do it computationally, numerically, and we started to see this technique where you discretize space, discretize time, and you take these little steps to time, tracking the trajectory, the XY coordinates or the theta coordinates of the projectile or the pendulum. So that's what we're doing. But each time we take a step, we've got to, the key thing is we've got to update the position and the velocity of the particle. And we want to know how to update the position and velocity of the particle. Because I said there's a problem with the way we updated the position and the velocity of the particle. My little example, it has an error in it. It doesn't account for velocities or accelerations that are changing with time. And that's a real problem. That's a catastrophic problem if you try to do the pendulum motion, for example, where there's change in acceleration. Okay, so that brings up, this is very fortunate. Taylor, you probably met, I assume you met Taylor expansion, Taylor approximation. It's an expansion approximation for the value of a function at some point. Based on the value of the function at another point, so normally we say the origin, but another point, and the first, second, third, so forth, differentials, so the slopes of 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 that function at the origin. So that's what the Taylor expansion is about, the Taylor approximation is about. And we want it now in computational physics, in numerically solving things. Now we got computers. But you know, interestingly, it's been around for hundreds of years. Taylor was around 300 years ago. I put it in a book. Anyway, but what it describes is the following problem. Here's some variable, independent variable. Here's some constant, dependent variable, and we're told that we know the function, say, at the origin. And we want the function at this location that's away from the origin. And the Taylor approximation, Taylor series tells us how to calculate that. Well, isn't that exactly what we want to do in our code? We want to calculate the future position and velocity of the tennis ball or the projectile, based on the current position and velocity of the projectile or tennis ball. So the position and the velocity are some function of some independent variable, time, and we know them at the current time. You know the position, the velocity at the current time. We want to calculate the position velocity at this future time. So this Taylor expansion, Taylor approximation is describing exactly the problem that we want to solve. And so we're going to, when we go back to solving differential equations, we're going to be using the Taylor expansion, Taylor approximation to improve our methods and develop our methods. But I just wanted to introduce it here. So this is the Taylor expansion. You know, if you want to know the value of the function here, and you know the value at x, and you know the value of the function the origin, well, the first sort of 0th level estimate is, well, it's the same. If it's nearby, it's probably quite close to being the same. If you want a first order estimate of what that function is at x, based on what it is at the origin, well, it's the value at the origin with a little correction. That's based on the slope that you observe at the origin. This is the differential of the function, this notation here, times your separation from the origin. This is what we were using in the code, right? For the functions of the position and the velocity, we were using the slopes of the position and the velocity to update the positions and the velocity after some time interval. So we were using this first order estimate.
But the Taylor expansion approximation gives us a whole series of different orders of estimates. This would be the second order estimate. So second order estimate, saying that if you want the function, the value of the function x, and you know the value of the function at the origin, then, well, the first sort of correction is for the slope here at the origin, so we make a correction for that. But then the second order correction is a correction based on the slope of the slope. If you see that that slope is changing at the origin, well, you can make a correction based on what that changes at the origin. And so that's this second order correction. And so on and so forth, right? If the slope's changing, you can make a correction for the rate of change of the slope. If the rate of change of the slope's changing, you can make a correction for the rate of this change of the slope changing, and that's this correction here. So it's a rigorous path to make a more precise estimate of the future velocity and position when you know the current velocity and position if the velocities and positions themselves are changing in time. So it's exactly what we want for our approach. I'll skip that, but I just wanted to show you, end up with a couple of examples here. It's also interesting, the Taylor expansion is also interesting, not just for our numerical computational simulations that we're going to be doing, and the trajectories, the paths of projectiles or pendulum, but it's also interesting in, if you think about a computer, well, how could that computer, we use it to calculate the cosine of an angle, the sine of an angle, or we use it to calculate the exponential of a number or the log of a number. And how can a computer calculate that? One way it can calculate it is based on actually Taylor approximations, Taylor expansions for those functions, for trigonometric functions or exponential functions. So I just wanted to show you an example of that. Here's our Taylor expansion. It says that the value of the function at x is the value of the function at the origin plus these corrections that involve the must be straight here. Yeah, there's a mistake in this line. I got a typo in there. I have to correct that for it. What have I got? Let's take a look at this line. Want to calculate the value of the function at x is the value of the function of the origin with a correction based on the slope, with a correction based on the slope of the slope, and so forth. Let's apply the Taylor expansion to calculating cosine x. Right, so let's think of the function cosine x. Cosine x, it's here's the function. Its first differential is minus sine x. Its second differential is minus cosine x. Its third order differential would be back to sine. It would be sine x. So we can calculate all the differentials for sine x. We can therefore easily calculate the values of these differentials at zero. And this is basis for the expansion, the Taylor series expansion, or the Taylor approximation expansion for cosine x. So if you just fill in these values for the differential was evaluated at zero. Sorry, there is a typo. There's a missing term at the end. You get this sort of sequence for cosine. So this is how to write cosine in terms of a power series in x. You can do this for sine as a power series in x. That's the homework assignment. You can do it for exponential as power series in x. And then you can use a for statement, for example.
to sum up the terms in the power series and calculate the value of a cosine, or calculate the value of the sine, calculate the value of an exponential. And so this is another example of a use in computational work of Taylor expansion. Taylor approximation is to calculate the functions that we use in our work, cosines and sines and exponentials and so forth. And you can calculate them as a series with a for loop. And as I say, this is the one of the assignments. I did it. I think the assignment is to calculate the sine of x. I did actually do this homework, and here's a little video of calculating the sine of x. The green line is the blue line is the sine of x, and the red line is going to be my calculation as I calculate it for more and more terms in the Taylor approximation, in the Taylor expansion. And so as the video rolls on, you'll see the number of terms that I'm using. Right now I'm using no terms, is going to change. And it's just using the Taylor expansion formula that I introduced. So that's the first term. The first term for sine is just the sine x equals x. It's the small angle approximation. This is if I include the first two non-zero terms, first three non-zero terms, first four non-zero terms, and so on and so forth. It's really kind of interesting to me that it's sort of, there's always a region where it looks like it's really good approximation. Then there's a region where it becomes a really bad approximation. It's a very definite step from a good approximation to a bad approximation. It just walks outwards as you include more and more higher powers in the Taylor expansion, Taylor series for sine x.